Hello everyone, I'm Vic, and today I'll be presenting Quicksand, harnessing stranded data center resources with granular computing. This is a joint work with Zane, Kaiyan, and Adam from MIT, Marcus from VMware Research, Sojan from USC, and Malte from Brown. Data center applications today use varying amounts of resources over time. On any given server, as one resource becomes the bottleneck, others are left idle and cannot be utilized, leaving resources stranded. Over time, different resources can become the bottleneck, causing different stranded resources on a server. In this work, we focused on solving stranded CPU and memory, but stranding is a general issue for many data center resources, such as device IOPS and GPUs. Resource stranding is a common challenge faced by data center operators. For example, Azure reports that more than 30% of memory can be stranded if CPUs are fully utilized, and Alibaba Cloud says more than 30% of their CPUs are stranded. Throughout the talk, I'll use the red boxes and red X's to indicate where stranding happens. Stranding is a costly concern for cloud operators because they have already paid for the hardware resources, but cannot monetize on them due to stranding, leaving money on the table. In this work, we asked the question, how can we enable applications to use stranded resources? To answer this question, let's first take a look at the status quo. Today's data center applications are deployed in coarse-grained units, such as virtual machines, which are scheduled to a cluster of physical servers. As the application scales up, the application creates more VMs. Even if the cluster has enough idle resources in aggregate, as highlighted by the two green boxes, the resources may be stranded across servers. For example, server 1 has enough memory but not compute, leaving memory stranded. And server 2 has enough compute, but not memory, leaving compute stranded. Memory disaggregation is a promising line of work that solves stranded memory by transparently pulling them across servers. However, the transparency comes at a performance cost. Because any memory access can be local or remote, it is challenging for developers and systems to optimize based on memory access patterns, introducing non-negligible overhead. As a result, memory disaggregation can unstrand memory, but at the expense of application slowdowns. In contrast, there's a recent line of work called granular programming that makes local versus remote accesses explicit. In such frameworks, developers break their applications into small units, shown by the mini boxes on the left. Memory accesses within a unit are local, and cross-unit accesses may be remote. One may think that granular units can solve stranding because, as we have shown, coarse-grained units, like virtual machines, suffer from stranding. In particular, a prior granular programming framework called NU sounds promising because it allows applications to shift resource usage across servers interchangeably via migrations, for example, in response to resource pressure. However, even though fine granularity makes migrations fast, it does not solve stranding because fine-grained units still couple resources. For example, NU cannot migrate to the top server because it has fully exhausted its memory, leaving CPU stranded. We observe that resource coupling is the main culprit behind stranding. Once a resource is fully utilized, no additional unit, however small, can be scheduled on that server. In this work, we try to do resource disaggregation in the programming framework layer via granular programming. Specifically, we observe that if we can decompose applications into small units that each use one resource, then we will be able to solve resource stranding. If each unit only uses one resource, then the scheduler can avoid stranding with a very simple, for example, greedy algorithm. The scheduler identifies idle resources in a cluster and continues scheduling until all resources on a server are exhausted. Moreover, fine-grained units allows to fill all stranded resource gaps, even very small ones. Therefore, the key insight of our work is that decomposing applications by fine-grained resource decoupling unlocks stranded resources that are previously unusable. The approach we take in this work is to unstrand data center resources without physically disaggregating them. Rather, if we can decompose applications into fine-grained units that each use one resource, we can disaggregate at the software layer via granular programming. In the rest of the talk, we introduce Quicksand, our realization of this idea. Quicksand is a new granular programming framework that unstrands resources. We have three goals when designing Quicksand. First, it should be able to use stranded resources wherever and whenever available in a cluster, even for a brief period of time. Second, it should be general and support both batch and latency-sensitive applications. Third, it should be easy to use, adopt, and deploy on hardware today. Realizing Quicksand requires us to solve three main challenges. First, how do we actually decouple compute from memory, given our computer architecture today, where data and instructions are tightly intertwined? To address this, Quicksand proposes resource proclets, which are granular units that primarily, but not exclusively, use one resource. The second challenge is to decompose application logic by resource. This is hard because application developers are accustomed to thinking in high-level logic, not in terms of how to structure code in a resource decoupled manner. To address this, Quicksand provides high-level frameworks that automatically decomposes into resource proclets, while retaining the programming flavor of a traditional C++ application. Third, resource proclets need to migrate to use stranded resources across servers, but they need to be fine-grained to keep migration time low, which is critical for latency-sensitive applications. However, units that start out fine-grained may become big over time due to memory allocations and workload challenges. Our solution is to dynamically split and merge resource proclets so that they can be migrated quickly without application performance impact. We introduce Quicksand by first introducing resource proclets. To do so, I'll first give a short introduction on proclets, which are the granular units featured in NU. NU decomposes the traditional Unix process into small units, each with a heap and a stack. Proclets can be placed on different physical servers, making the application distributed. Quicksand decouples compute and memory by breaking NU-style proclets into compute and memory proclets, respectively. These proclets are what we call resource proclets, which are units that primarily use one resource. Specifically, a compute proclet is analogous to a thread, but it still uses a small amount of memory for its stack and transient allocations. A memory proclet is akin to a small heap region in the order of megabytes, but it still uses the CPU for loads and stores. Quicksand provides the option to temporarily pair memory and compute proclets together, forming hybrid proclets. This is helpful for sections of code that are memory access intensive by co-locating compute and memory. However, because hybrid proclets reintroduce stranding, Quicksand applications use hybrid proclets sparingly, and we confirm so in our application case study. Resource proclets form the basis of the Quicksand architecture. To facilitate their use, Quicksand provides a number of high-level frameworks that automatically decompose application logic into resource proclets. This includes the batch compute framework, similar to MapReduce, sharded data structures, similar to C++ standard library, and a services library useful for implementing microservices and serverless applications. Application developers only need to interact with these frameworks without needing to manage proclets. Internally, an auto-sharding layer manages proclets and splits and merges proclets to keep them fine-grained. Finally, the Quicksand runtimes schedules and migrates proclets and monitors their usage to make sure that they're primarily using their intended resource. To see this architecture in action, let's use Quicksand for a popular workload, training data preprocessing. This is a high-level overview of the data preprocessing pipeline. We're processing images in a disaggregated fashion, where CPU servers resize, rotate, and denoise images before they arrive on the training GPUs. Realizing this pipeline in Quicksand requires only a few lines of code. The first line loads unprocessed images into a sharded vector. The second line creates a sharded queue, and the rest of the code processes each image and enqueues them into the sharded queue. The queue is consumed by GPU servers, which is not shown in the code snippet here. This style of programming feels similar to programming with C++ standard library APIs. However, it disguises the fact that Quicksand automatically decomposes the application into memory and compute proclets under the hood. With this code in mind, let's see how the overall pipeline decomposes into resource proclets. Images are first inserted into a sharded vector consisting of many memory proclets. They're then processed by compute proclet workers, which pushes processed images into a sharded queue, consisting, again, of many memory proclets. With this high-level view in mind, let's see how resource proclets interact with one another by zooming into the first phase of the pipeline. The application first uses Quicksand's For All API and its batch compute framework, which asks for a function and a data range to compute over. This is similar to the map phase in MapReduce. Internally, the batch compute framework spawns compute proclets based on the cluster's available compute. Each compute proclet is assigned a disjoint data range to compute over. The application can then seal the sharded vector, which marks its data as read-only, and make it available for prefetching. When iterating over the sharded vector, Quicksand prefetches sealed data in the background to overlap compute with memory accesses, hiding access latency. Memory proclets support custom prefetching logic that is informed by data structure semantics. For example, an ordered data structure, like the sharded map, can prefetch based on key order rather than memory locality. This differs from hardware prefetchers, which rely on memory layout, or page-level prefetching in memory disaggregation, which results in amplification. Quicksand's auto-sharding layer splits and merges compute proclets to adapt to changing load and resource availability. In this pipeline, it monitors load by observing the length of the sharded queue. If the queue is draining fast, that indicates that GPUs are consuming images faster than they're produced, risking GPU stalls. Observing this, Quicksand splits a compute proclet if there are idle CPU cores, increasing the production rate by using one more core for processing. Quicksand can split the work of a compute proclet because each proclet is responsible for a distinct data range. In general, the high-level frameworks use compute proclets in such a way that fine-grained compute work, such as loop iterations in a traditional application, can be split in Quicksand. Quicksand continues splitting in a control loop until production and consumption rates match in this application. It also splits based on other signals, such as in the presence of a compute proclet straggler. Next, let's take a look at the second phase of the pipeline. Compute proclets push to the last memory proclet in the sharded queue, where each proclet represents a shard. As more data items are inserted, the tail memory proclet uses more memory. To maintain fine granularity, the auto-sharding layer limits memory proclet's heap size to a maximum, for example, 16 megabytes shown here. As data is inserted, the memory proclet is split into two, creating a new tail memory proclet. The next push resumes at the new tail. In this way, sharded data structures can keep memory proclets fine-grained via splitting. Conversely, memory proclets also merge when they become too small. Finally, let's take a look at how Quicksand can deploy this pipeline to use stranded data center resources. Quicksand initially allocates memory proclets to store unprocessed images in the sharded vector. Since the cluster has idle memory on all servers, Quicksand can place them across the servers. Next, Quicksand's batch compute framework spawns compute proclets to do image processing. Quicksand schedules compute proclets on both servers and fully utilizes the CPU on the bottom server, resulting in stranded memory. As Quicksand stores processed images in the sharded queue, it is able to use stranded memory effectively because the application is already decomposed into resource proclets. Finally, in reaction to resource demand from collocated workloads, Quicksand can migrate resource proclets precisely in response to the resource under pressure, enabling Quicksand to quickly adapt to collocated workloads. Therefore, by decomposing applications into resource proclets, Quicksand can utilize stranded resources productively. We believe that Quicksand's fine-grained resource proclets make it possible to fill almost all idle resource gaps, leaving no compute and memory idle in the data center. We implemented Quicksand about 10,000 lines of code on top of new and Calda. We ported 4 applications to use our Quicksand libraries, including batch processing and latency critical workloads. We found that applications only need to modify a few lines of code to adopt Quicksand, and that hybrid proclets are only needed in the sorting workload. For evaluation, we asked the following questions in the paper. Does Quicksand unstrand resources better than existing solutions? Can Quicksand respond to changes in resource availability and demand? Do resource proclets separate the use of different resources? And does Quicksand's rapid scaling and fine granularity improve utilization and performance? For this talk, we'll focus on the first question, whether Quicksand unstrands resources better than existing solutions. To answer this question, our experiment consists of 3 setups that contain the same amount of idle resources. The first setup uses 3 idle servers. Next, we have 2 setups with twice the number of servers, but with the same amount of idle resources as the first setup. The 2 setups introduce imbalanced CPU and memory usage, respectively. Note that the sum of the idle resources across the two setups on the right are the same as the balanced setup on the left. We compare Quicksand to two baselines: Hermit, a state-of-the-art memory disaggregation system, and Nu, a granular programming system that couples CPU and memory. This figure presents the throughput of the training data preprocessing pipeline. In the memory unbalanced setup, Hermit can use stranded memory across servers through paging, but paging introduces non-negligible overhead, resulting in 17% lower throughput compared to Quicksand. Nu only achieves half of Quicksand throughput because it cannot use stranded memory due to resource coupling. In the CPU unbalanced setup, Quicksand achieves 2 times the throughput compared to both baselines. This is because neither memory disaggregation in the case of Hermit nor granular units in the case of Nu unstrands CPUs. Quicksand even outperforms baselines by 8% in the balanced setup because it splits the right number of compute proclets to match available CPU cores. In contrast, both Hermit and Nu spawn a large number of user-level threads, causing excessive context switching and poor cache behavior. There are more evaluation results in the paper. This includes showing Quicksand can scale in millisecond scale in response to changes in resource availability as well as the workload. We also show that resource proclets can effectively separate the use of compute and memory, as well as the benefits of keeping proclets fine-grained. To conclude, we have presented Quicksand, a new programming framework that addresses resource stranding, a major source of inefficiency in today's data centers. Our approach is to solve stranding in software rather than physically disaggregating in hardware. Our key insight is that we can unstrand by decomposing applications into fine-grained units that primarily use one resource. We show that this approach unlocks stranded resources that are previously unusable in various workloads in our evaluation. We open source Quicksand at the following URL. Thank you for listening, and I'm happy to take any questions.